Our work for this course is an unpaired GAN model for MRI reconstruction with parallel imaging data. Existing works for general super-resolution tasks are all paired because it's hard to generate highly accurate images without pixel-wise or perception loss. Unpaired input and label for training is only possible with pure GAN loss. The reducing supervision makes our approach challenging, but it's preferred by radiologists and useful in the cases where we have limited or no labels for certain datasets. Finally, despite the more difficult settings, GAN training gives output that have more realistic texture than outputs from models trained with pure pixel-wise loss. Compared to many other GAN applications for MRI reconstruction, with a novel data consistency layer, our label makes use of all information collected by the parallel imaging method instead of just the undersampled images. So our model is capable of recovering 7-fold undersampled data, comparing to 3-fold from the baseline model. And our model works with raw data, making it closer to real-life application. We designed a new data feeding pipeline for multi-channel complex value data, while the baseline model uses a built-in JPEG decoder from TensorFlow. This figure in the sagittal view illustrates two problems from the baseline model. One is the missing bright regions due to converting to JPEG. Another one is the vertical artifacts from the synthesized input in the first row, which is barely noticeable in our case. Here is the training flow of our model. The input to the generator is an undersampled blurry image X. The output of the generator goes to the DC layer, whose output serves as the fake input to the discriminator, while the fully sampled image Y serves as the real input to the discriminator. Notice here X and Y are not from the same object, because our model is unpaired. The generator is a 7-layer ResNet and the discriminator is a 7-layer CompNet. We use WGAN GP as our training objective. The DC layer combines the undersampled K-space measurement and the K-space of the generator output, making sure our final output is consistent with the measurements, and it's important for stabilizing the performance of our generator in this low supervision setting. Our new DC layer takes in more information. Capital Y here is 8-channel measurements instead of the 1-channel capital 1 in the old DC layer. Then we also make use of an extra 8-channel sensitivity map S. Now I will show our results in the way as radiologists looking at scans. From left to right are 7-fold undersampled input, model output when trained with 1/6 of the labels, model output when trained with 1/3 of the labels, and the ground truth. First on the axial view, where our training is done. Then on the sagittal view, finally on the cornel view.